we're going to start the gas laws unit. So the gas laws unit obviously has to do with gases. Hopefully you've seen the video or the demonstration regarding gas laws and the three variables involving the gas laws. You are somewhat familiar with the gas laws formula, so you're in good shape here. So we're going to talk in this in this lesson a little bit about the difference between real gases and ideal gases. So we're going to talk about ideal gases and what they behave like, and real gases and where they behave like ideal gases. We're also going to talk about the kinetic molecular theory. The kinetic molecular theory, as it applies to gases, is important to understand. So when we start talking about gases and we start talking about the kinetic molecular theory, we understand what we're talking about because we have a basis of understanding. So that brings up the idea of an ideal gas versus a real gas. Well, an ideal gas, as the phrase, as the term sounds, an ideal gas is a gas that is perfect. Well, therefore, if it's perfect, there's no real ideal gas because they're unattainable. There's always some kind of imperfections. But what we're talking about here is what people consider, why would we even talk about something that's not even real? Well, the reason we're talking about it is because most real gases are all our known real gases. So everything we know as a real gas, those are real gases. All real gases, all right, they behave as though they are like an ideal gas. So in normal Earth conditions, low pressure and high temperature, our Earth is relatively low temperature, or excuse me, relatively low pressure and relatively high temperature. Real gases act like ideal gases. Places like Jupiter, where you have extremely cold temperatures and extremely high pressures, well, their gases are actually liquids. And why is that? Well, it has to do with what the difference is between a real gas and an ideal gas is. A ideal gas, right? In an ideal gas, those particles, there's no volume. So if you think about that, that doesn't make really sense. They have to have it because they exist. Well, again, we're talking about an ideal gas. Those particles act as though an ideal gas would have particles that have no volume. An ideal gas would have particles that have no attractive forces between them. Now, you know that real gases, they don't have strong attractive forces between them. They have the London dispersion forces, and only when they become really close do those very weak London dispersion forces start to show up. But in an ideal gas, there are no attractive forces between the gas particles. And then the last part is that gases, an ideal gas, could be compressed all the way down to zero volume. Because the particles have no volume, there's no attractive forces, you can compress those infinitely all the way down to zero. Well, as it turns out, real gases don't behave that way. At normal Earth conditions of low pressure and high temperature, real gases will act as though the particles have no volume. They will act as though the particles have no attractive forces between them, and the particles will act as though they are infinitely compressible. But in reality, a real gas will condense to a liquid at high pressure or low temperature, or both conditions. Think about a propane tank. A propane tank has the propane in there. It's a propane gas under high pressure. There it changes to a liquid. It's now liquefied propane, LP gas. Real gases will condense to a liquid at high pressure and low temperature. Real gases, as said, they deviate from ideal behavior at high pressure and low temperature. That phrase, real gases deviate from ideal behavior, that is an important concept. Understanding that under which conditions real gases will deviate is an important idea, meaning they will no longer act as though the particles have no volume. They will no longer act as though the particles have no attractive forces. They will no longer act as though they are infinitely compressible. They deviate from that behavior and they condense into a liquid. That's the difference between a real gas and ideal gas. So this brings up the kinetic molecular theory of gases. So we know that kinetic, the phrase kinetic energy, or the measure of the average kinetic energy, that is temperature. So temperature is one of the variables that affects gases. The three variables that affects gases are temperature, pressure, and volume. Those three variables, they are interrelated, and as such, there's a gas law for them. Well, the kinetic molecular theory of gases has to do with ideal gases and their deviation from it. So the kinetic molecular theory states that gases are composed of individual particles moving in continuous straight lines. So if you consider a gas particle, it's going to be moving along inside a container. It's moving along in a straight path, and when it just going to keep going until it comes in contact with something or something, whether that something is another gas molecule or that something is the sides of the container, it's going to continue in a straight path. When it does, it's going to bounce off that. And when it bounces off, there's no energy loss. It's going to be a perfectly elastic collision. So when it bounces off, it's just going to bounce in which angle it's going to take is going to have dependent on which direction it was going. So it's just going to bounce off perfectly elastic. There's no loss of energy, and it's going to again continue on in a straight path. As it continues on a straight path, it may run into another particle and bounce off that one again, losing no energy, a perfectly elastic collision. The kinetic molecular theory says that gas particles are so small that their volumes are considered to be zero or negligible. They're so small relative to the space they're contained, it acts as though they have no volume. So if you think about a gas molecule versus a container, the container is mostly empty space, whereas the gases are bouncing around inside that. Their particles, their molecules are taking up hardly none of the volume of that space. So that's why their gas particles are considered so small that their volumes are considered negligible. And then the last part is the particles have no intermolecular forces of attraction. For all intents and purposes, London dispersion forces are so weak that they act as though those particles have no intermolecular forces of attraction. So with this theory that how the ideal gases are created or how real gases behave, this is how we're able to use the kinetic molecular theory of gases. This is how we're able to use the ideal gas laws, because these traits right here hold true for real gases, because real gases have virtually no intermolecular forces of attractions. Real gases are relatively small volume compared to their, or small or no volume compared to their container. And then when they bounce off things, they bounce in perfectly elastic collisions. No energy is truly lost in the collision between gas molecules. All right, so now you're going to work out a couple questions, and then we'll get back to lesson 2.